All right, everyone, good morning. Thanks for coming. So today I'll go over an example Hess's Law problem, and then we'll review for the exam. So the exam is this Saturday, just like we did for test 2, which seemed well. I didn't see any big disasters, so let's continue that trend. Hopefully, crossing our fingers, no disasters, but this Saturday will be the exam. After I go over this problem, we will go over what to study for the exam. The exam will cover chapter 5 and 6. All right. As part of your exam, there will be a problem with Hess's Law. So this is what Hess's Law is all about. This is what Hess's Law is all about here. I'm going to give this to Adriana. Pass it down. So we'll do a practice problem, and then we'll review for the exam this Saturday. So Hess's Law will be a type of problem that will be on the test. The idea is that we have a target reaction. Okay, we have a target. Target. So this is the reaction that we want to compute the enthalpy of. Remember what enthalpy is? Okay, it's a heat flow. Okay, is heat coming from the reaction to the universe, or is the universe giving in heat to the reaction to make it go? Okay, all of that is symbolized by this idea of enthalpy. All right, so here this is enthalpy. I don't know if you remember from last week, we can measure enthalpy at what's called the standard state. A very specific set of conditions. And then we can also measure the enthalpy of forming 1 mole. Okay, that's what we look up in the back of the book, standard state formation. This particular problem with regards to Hess's Law is looking at just, non-standard state conditions. Just plain old delta H. And this is our target. Well, what do we have with our target? Okay. Okay, we have 3 reactions that we do know. 3 reactions that we do know the enthalpy of. Right? So this is how I'm your teacher, so someone may tell you a different way, but when I tutor and do all this other side stuff, this is what I tell my students. So same thing I'm going to tell you guys. So here's our target. Notice here that we have 3H2O on the product side of this ledger, of this equation. And let's call these reactions that we do know the enthalpy of 1, 2, and 3. Okay, I got 3H2 in my target. Here, reaction 2, I got 3H2 on the product side. Okay, so I'm not going to do anything with reaction 2. Why? Because 3H2 is on the product side. And look here, N2 on my target that I want to capture the enthalpy of. That's also in my product side in reaction 2. So I'm going to leave reaction 2 as is. Okay. Now let's look in the green here. In the not the green. Let's look in the purple here. In the box, I have CH2O gas. That's on my product side. But look where it is in reaction 3. Okay, it's on the reactant side. Yeah, very good. So the first thing I want to do is I want to flip reaction 3. Okay, so I'm going to reverse reaction 3. Okay, I'm going to flip reaction 3. I'm going to reverse it. So let's do that. So what becomes product now is our reactant, CH4O liquid. Okay, that's going to go to CH2O gas plus H2 gas. Okay, again, please realize, why am I flipping it? I'm flipping it because now my CH2O product side is on CH2O product side. Now when we flip it, we flip the sign of the delta H. So this is something I want you guys to know. When we flip the reaction, we flip the sign. So what was once endothermic now becomes exothermic. You see here? CH2, CH2. I got my CH2 in the product now successfully. My N2, 3H2s on the product here in reaction 2. So I'm going to do step 2 here. I'm going to add reaction 2 to this. Unchanged, do absolutely nothing to it. So that's going to be 2NH3 gas goes to N2 gas plus 3H2 gas. Unchanged, so that's going to be 57.5 kilojoules. All of this is in kilojoules now. Okay, what do you guys see here? Target, I have N2H4 liquid and CH4 liquid. Here I have the CH4 liquid, so that's in the reactant side, right? The target. So here I got it in my reactant side because I flipped it. NH4, so check. The NH4, here it's on the product side, and in the target it is where? In the target it is in the reactant side. So what shall we do to reaction 1 here? Flip it or reverse it. Very good. So we're going to reverse reaction 1. So what becomes products now becomes reactants. What becomes reactants now become products. So flipping that, we're getting NH, flipping that, excuse me, I'm getting N2H4 liquid plus H2 gas goes to 2NH3. Okay, flipping that, I flip the sign, so now it's no longer 22.5, but minus 22.5 kilojoules. And now, okay, hopefully you can see the rationale here. N2H4 reactants, CH4 reactants, CH2O products, N2 product, 3H2 product, 3H2 product. Okay. Another thing that we can do is we can cancel stuff out. So here, the 2NH3 on the reactant side cancels out with the 2NH3 on the product side. And anything else that you see gets canceled? Yes, very good, Joshua. H2 and H2 cancel. So we are left with the net, which is N2H4 liquid plus CH4 liquid, CH4O liquid, sorry. And that's going to go to CH2O gas plus N2 gas plus 3H2 gas. So what is our final answer? Our final answers are target. What is the enthalpy of that target? You just add them up. Okay, it's going to be minus 81.2 plus a 57.5 plus a minus 22.5, and all of that, do that on my calculator, I'm getting minus 46.2 kilojoules. So this net target reaction is exothermic. How do I know it's exothermic? I know it's exothermic because of the negative sign. The negative value tells you that it's exothermic. So that's how you do a Hess's Law problem. You notice how to solve this problem, we flipped reaction 3, kept reaction 2 the same, and flipped reaction 1. And then, as Josh mentions, the H2 cancels out, the 2 NH3s cancel out. All we got to do now is add everything up. So something like that on the exam, except you won't have 3 reactions, you'll probably have 2 reactions. So it's even easier. You'll have 2 of these to get your target. So that is Hess's Law, example problems similar to which that you will find on Saturday's exam. So let's quickly go over this exam. That will be this Saturday, so just reserve maybe 2 or 3 hours on Saturday for this exam. Yes, yeah, okay. Quiz also due Saturday. Very good. Let's get everything. So, yeah, let's get everything sort of squared away. Saturday will be your exam. Okay, so it's going to be 15 multiple choice and then a problem set. Okay, 15 multiple choice questions and a problem set. Okay. So that's on Saturday. So it's going to be open Saturday. And once you log in, you have 2.5 hours to do it. So there should be enough time. Hopefully there's no internet outages and stuff. Okay, the problem set will be open on Thursday. What is Thursday? Thursday is the 22nd. So you have a couple of days to do that problem set, and make sure you upload it to your Canvas, and I'll grade it. And as Adriana said, quiz 3 is also due Saturday. Okay, the way my system works, the test day is also the day your quiz is due. I also drop one of the 4 quizzes just as a reminder. So let's go over some of the questions that you will encounter, the types of questions that you will encounter. So before we review the exam, Wednesday and Thursday will be the last 2 labs, not last 2 labs. The lab that you'll do with me and Larissa is solubilities. Solubilities within a family. And then the lab, you can get a head start. I usually close my lecture with the semester on this, but your computer lab is going to be molecular models. Okay, where you actually build some molecules. So my lecture for that is 9 and 10. I lecture that as a unit, so you'll probably have that in a couple of weeks. Okay, so if you want to get ahead, you can work on that, but my lecture is going to come a little bit later. Okay. And that will be the labs, end of the labs. I do have some extra credit labs up on Canvas that you can check out for some extra points, so if you want to do that, you can. All right, so Chapter 5 and Chapter 6. Chapter 5 is gas laws. Chapter 6 is energy. So let's talk briefly about Chapter 5. So let's say we have a problem here, an equation. And so remember, these are all gases. CH4 is a gas, O2 is a gas, CO2 is a gas. Water is typically a liquid. So let's say from this balanced chemical equation, so let's say I have my calculator. Okay, let's say I have 15 moles of CH4. Okay. And now the question, typical question may ask you, okay, what is the volume of the CO2 product I get, if this reaction is done at a temperature of 23 degrees C and a pressure of, let's just say, 0.985 atmospheres. So how will you go and approach such a problem? Okay, so if they're giving you 15 moles of CH4, okay, and we want to figure out the volume of CO2 that is left as a product. So what is our rationale? Okay, well, remember, gases have an ideal gas law, which is PV equals nRT. So this is what we want to find, and it's for CO2, okay, not for these other gases. We have our pressure, we have the temperature. What do we always have to do with our temperature with gases? Always, yeah, like automatic. It's going to be 296 Kelvin, so we'll add 273 to that to get 296 Kelvin. We got our pressure. R, I'll give you R. Okay, so you do not have to worry about that. Give you R. So we need volume, but we also need N. So how will we capture N? Well, this is pretty straightforward because you see in this problem, if you start out with 15 moles CH4 type of problem you'll see on the exam, the equation is balanced, so that's good. Okay, make sure your equation is always balanced. So 15 moles of CH4, we know that for every 1 mole of CH4, because this equation is balanced, for every 1 mole of CH4, there's 1 mole of CO2. So that means we should get out 15 moles of CO2. For every 1 mole of CH4, there's 1 mole of CO2. So for every 15 moles of CH4, there's 15 moles of CO2, again, because it's balanced. So that is our N. And now we have everything to solve this problem. So we'll isolate V. V is equal to nRT over P. Our N here is 15 moles of CO2. our universal gas constant will be given to you. So 0.0821 liters atmosphere over mole Kelvin. So over mole Kelvin I'll put in the denominator. T here's your temperature. Well, you guys already know that it has to be in Kelvin. And the temperature in Kelvin is going to be 296. Okay, divided by P. The P was given to us in this problem as 0.985 atmospheres. Okay, so I did not bring my calculator, I guess. I do not see it. So we'll just make sure you know how to do this on the calculator. One final thing, units. Moles cancel. Atmosphere cancel. Kelvin cancel. And I'm left with liters volume. Okay. So whatever that answer is. And like I said, unfortunately I didn't bring my calculator. Anybody have an answer? Josh, you got an answer?
I got
370 liters? Okay. Sounds about right. Okay. All right, so a problem like this on the exam. So not only this, but also the problem set. Okay, so what I'm saying is that multiple choice and the same type of problem in the take-home problem set. Okay, so same theme. Okay. Now the problem set, make sure you show all your work, show all your steps for full credit or partial credit also. Also talking about the chapter 5, there's one concept here known as STP. Okay, so STP, should know what STP means. Two important things. First important point on STP is that it's just a temperature and pressure. Okay, it stands for standard temperature and pressure. So in STP, what is your standard temperature? It's going to be 0 degrees C. You guys remember that? Okay. But again, because it's gases, we're not going to put degree C. We're going to put 273 Kelvin. So that's your standard temperature in STP. Your standard pressure in STP is 1 atmosphere. Okay, so that is what STP stands for. And that is all, and that is it. Okay, nothing more, nothing else. Well, it just so happens that if I have 1 mole at STP, okay, if we have 1 mole of an ideal gas at STP, if we have 1 mole of an ideal gas at STP, that means we have 22.4 liters volume. Okay, but 1 mole and 22.4 are not your STP. Okay, what is STP? It's just standard temperature and pressure, and that's it. It's just a temperature of 273 Kelvin, and it's just a pressure 1 atmosphere. It just so happens that no matter what gas, how heavy, how small, how healthy, how unhealthy, if you have 1 mole at STP, you're at 22.4 liters. Well, remember the STP box. You need 1 mole, okay, but 1 mole is not STP. And Also, some of the gas, there's the ideal gas equation, right? PV equals nRT. But then there's also these sub-laws. So what do I mean by the sub-laws? I'm talking about things like Boyle's law. So Boyle's law is if you increase the pressure of something, you decrease the volume. And that's the only sub-law that's inverse, or what is that? Indirect. Okay, one goes up, one goes down. This is called Boyle's law. Okay, we're talking about how ideal gases behave. Ideal being the common word. But there's also other laws here. As an example, if you increase the temperature of a gas, the gas expands. The gases, increase in volume. So that's one version of Charles' law. And also, if you increase the temperature, the gas molecules collide more, right? The gas molecules hit each other more. Is it not so, Adrienne? They hit each other, collide more. So more collisions means more pressure. That's also another aspect of Charles' law. What's important is that these are direct. As one goes up, the other also goes up. But Boyle's law, as you'll see, is the only one that is, as one parameter, pressure goes up, the other parameter, volume, goes down. That's an indirect relationship. And then there's one more. I always tell people blowing a balloon. Okay. Blowing a balloon, blowing a balloon, inflating a bicycle tire, inflating a basketball. Okay, so as you increase the volume, or as you increase the number of moles, you increase the volume. And that's Avogadro's, another direct relationship between one and the other. Okay, so just keep those in the back of your mind for the exam. The question here on enthalpy. So remember, there's like the enthalpy, that standard state. You'll see this in Chem 2, delta G naught, S naught. Okay, here's delta H naught. That means standard state. And then we have the delta H that you look up in the back of your book. That is not only standard state, but also forming 1 mole at standard state. This is something you look in the back of your book, okay, or you look up on the internet. Natural abundance baseline elements usually default to 0 for these guys. And then you have just plain old delta H, whatever conditions, whatever temperature, whatever pressure. So 3 different enthalpies. They're not, their meanings are different. Okay, one condition, another condition forming 1 mole, and then any old condition that's in the problem. Okay, that's in the problem that you're trying to solve. And having said that, we also are interested in signage. Signage means if any of these values is negative in sign, okay, that means usually that reaction is going to be exothermic. Exothermic, which means heat gets released. Okay. Heat, lowercase q, gets released to surroundings. Okay, and the surroundings is the universe. Just the reaction gives off heat. Okay. And so that's a negative sign, and then this heat is also in the product side of the reaction. Okay, it is a product. Okay, it's not, you get your products, but another product is heat. So that is any of these 3 values have a negative value, negative sign for their delta H. By the way, we usually say delta H of the reaction, because the reaction is what we're interested in. And totally the opposite situation if you're a positive in sign, and we call that endothermic. Okay, here heat is not released, but heat is absorbed or required. Okay, and heat is on the reactant side of the ledger, of the chemical equation. Make sure you are good with your signs. So we have heat, Q. We also have another form of energy that's kind of useful, and we're going to call that work, right? Work. Okay, so here we have signage also, but you got to look at the wording here. So here it's work done. Let's say it's done by me, so I'll say by the system. On who? On you guys. You guys are my universe. Okay. On surroundings. Surroundings are the universe. So in this particular case, the system will have a negative sign for work. They're both energies, work and heat, Q are energies, but this is energy that is useful. So that's going to be a negative sign. And the surroundings, same value but opposite sign. And then we have the opposite. Okay, the opposite scenario is this. We can have work done by who? By the surroundings. Okay, on who? On the system. Okay, so work, who's doing the work? The surroundings are doing the work. The surroundings here are going to be negative. And then the system, which is the recipient, takes that work, is going to be, the energy sign is going to be positive. Okay, so the way systems and surroundings talk to one another can tell you whether something is positive or negative. So again, these are all multiple choice parts for the exam. There's a problem here where you have PV equals nRT, which is the ideal gas law, but from here you can actually get the density of the gas. So I'm not going to go over that derivation, but the density of the gas and the molecular weight of the gas you can get. And again, like I said, I'm not going to derive it, but I will give you the equation. The molecular weight of a gas is going to equal to the density times R, all of that divided by P. Okay, so that equation will be given, but you'll just have to believe me that you can. I actually derived it in one of your quick videos if you're interested in how you can go from here to here, but as for the test, I'll give you the equation. So it's basically plug it in and get the answer out. So we can get the molecular weight of a gas. Okay, as an example, again, I don't have a calculator with me, but so let's say you are at STP. Okay, and let's say you have 0.400 grams of the gas. It occupies 0.280 liters of that it occupies, And then what does STP mean? Yes, and that also means 1 atmosphere and 273 Kelvin. So what's the molecular weight now? Given this information, similar to what you'll see on the test. What's the molecular weight? Well, what's density D? Density D is mass over volume, is it not so? Right, Kimberly? So density D is mass over volume. We got our mass, 0.400 grams. Okay, we got our volume, which is 0.280 liters. So whatever that is on your calculator. We have R, so I'll give you R, 0.0821 liters atmosphere divided by mole Kelvin. What's T? Well, it's STP, right? So T is 273 Kelvin. What's P? It's STP, right? So 1 atmosphere. So you can put all of those in here, and you should be able to get your molecular weight. Also, the units should all cancel out, leaving you with grams over mole. Okay, the units should all cancel out, leaving you with grams over mole. So I didn't bring my calculator, but whatever that answer is. So you're going to divide 0.4 divided by 0.8. That's your density. Whatever that value is, you put it here. You put R here. You put your T here. You divide it by P, which is at STP 1 atmosphere. All right, are there any questions on this? Let me go back. Are there any questions? Comments, questions? No? Okay. All right, there's an aspect on Chapter 6 where we can measure the heat of something. Kind of what you did in the lab, those of you that did the lab. Heat is lowercase q. How much heat is required to... I'm sorry. Strike this. How much heat is required to raise the temperature of a material? How much heat is required to cool the temperature of the material? All of that is in this equation, Q equals ms delta T. And S is your specific heat. Specific for 1 gram. Okay, that's the difference between specific heat S and heat capacity capital C. We're specific for 1 gram. So again, let's remind ourselves, it's the amount of heat in joules required. It's specific heat now, so specific heat required to raise 1 gram of a substance by 1 degree C. So let's do an example problem. So let's say I have a bar of silver coin maybe, or silver bar. Silver is Ag, that's the element on the periodic table. And the specific heat of silver is specifically a constant, so that's something I'll have to give you. So let's say it is okay, let's say it's 85.7 joules over grams degree C. Okay, I'll give you the real constant on the exam. Okay. So we can use this equation. Let's say we have, I don't know, 300 grams of silver. So my question to you is, how much heat is required to raise the temperature of 300 grams of silver? Let's say it's initially at 10 degrees and we want to raise it to 75 degrees. Okay. How much heat is required to do that? How much heat Q is required to raise 300 grams of silver initially at 10 degrees, taken out of the refrigerator, and raising it out to 75 degrees in the oven? Okay. So you can just plug everything in here, okay, and I'll give you this equation also. Okay, it's not, you do not have to memorize it. And so, a couple of key points here. Remember, delta T is final temperature minus initial temperature. Okay, final temperature minus your initial temperature. So let's say if, again, I do not have a calculator with me, but let's say you're heating this bar of silver, okay? Heating it. So what do you think your final answer will be, positive or negative? Heating. Okay, what are you doing when you're heating something? Are you adding heat to it? So if you add it to the system, silver, what will the Q be? It's going to be positive. Okay, what happens if you're cooling a heat, doing the opposite? You have a bar of silver that's 75 degrees C and it's going down to 10 degrees C. Okay, where is all that heat going? Where is it going? To the surroundings, Antonin, to the universe, to the surroundings, correct? So if you're doing that, then it's minus. Okay, so just have an eye on, if it's positive, or, I'm adding heat, the oven is adding heat. Okay, this, whatever is adding heat. If you're cooling, the heat's dissipating, and it's dissipating to the surroundings, so it's going to be negative. All right, so a problem like this, where you have to plug it in. There's this equation here. I just recommend, I refer you to the problems that are in Canvas, the little quick problems, 5 to 6 minute problems, but you'll have to calculate the delta H of a reaction and utilizing this equation. Products, sum of the products, okay, don't forget to multiply by the balanced coefficient, minus the sum of the reactants. Don't forget to multiply by the balanced equation. So I'll give you this equation, but you'll have to know how to use it. Don't get, math is a problem here, right? Don't make math mistakes. Okay, distribute that negative and all of that stuff. Okay, I don't have an example, but you can see the homework 6 example problems on Canvas. Okay. Sum of the products minus sum of the reactants. Say problem like that on the test. Couple of final points on Hess's law. So remember, let's say we have A plus B goes to C plus D, right? And let's say this delta H is 100 kilojoules per mole. This is just throwing it out there. Now, what if I ask you to compute the delta H for this reaction? 3A plus 3B goes to 3C plus 3D. What is our new enthalpy? I multiplied everything out by 3. 3A, 3B, 3C, 3D. What's our new enthalpy now for this new reaction? Yeah, it's going to be very good. Okay, you just take your enthalpy and also multiply by 3. Okay, so just remember that in the back of your mind. Also, Hess's law, okay, something like this. Okay, so Hess's law problem, you'll have 2 equations instead of 3 that you have to flip around and do some gymnastics. And then don't forget, you multiply an equation, you multiply the enthalpy. What happens if you flip it? You change the sign. So if I flip this, 3C plus 3D goes to 3A plus 3B. Adrienne is right, you change the sign. Okay. So what can you do? You can multiply it and you can flip it. Okay, that's what Hess's law is. And then you add it. Multiply it, flip it, add it to get to target. To get to the target. Okay, the last 5 minutes or so, that's pretty much it. There's one more problem with Boyle's law, a little bit more applied. Okay, so this is Boyle's law. P1 V1 equals P2 V2. Let me get this in a better color. P1 V1 equals P2 V2. So remember what happens in a Boyle's law or a Charles law or an Avogadro's law when you're blowing a balloon or inflating a tire. Things change. So let's say I have a volume of 6 liters and the pressure is at 1 atmosphere. Okay, just throwing some numbers out. All right, let's say I increase the volume. And so instead of 6 liters, I now increase it to 10 liters. I just expand the piston, I blow the balloon, whatever. Okay, I increase the size of the box so that now it occupies, instead of 6, 10 liters. Well, by doing that, what happens automatically? Automatically, I will get a new pressure, okay, P2. Okay, I will get a new pressure. Okay, so what is that new pressure? Okay, you're going to have to solve this equation. So here you just plug it in. So we have 1 atmosphere. V1 is 6 liters. Okay, P2 is something, the new pressure we have to solve for. Okay. V2, I expanded it from 6 liters to 10 liters. And then, yeah, all you got to do is solve for P2. So that's going to be 1 atmosphere times 6 liters divided by 10 liters. Okay, whatever that is on the calculator. That looks to be 0.6. Liters cancel. That's 0.6 atmospheres. Okay, I can do that math on my head. All right, so that's Boyle's law with real numbers. By the way, don't fall for this trick. Okay, if they ask you to convert it to millimeters of mercury, all you have to do, and I'll give you the conversion, it's going to be 0.6 atmosphere times 1 atmosphere is 760 millimeters of mercury. Okay, and whatever 0.6 times 760 is, I don't know that. Okay, that's the answer in millimeters of mercury. Okay, just getting you to change units. atmospheres cancel. You're left with whatever 0.6 times 760 is on your calculator. So, okay. On the test question, you may have to answer it in this unit, right? So if you have to answer it in millimeters per mercury, you'll have to use this conversion factor, which I'll give you the conversion factor. You do not memorize conversion factors. All right, so this is kind of what you'll see both on the multiple choice and the problem set. Don't forget there's a problem set. That opens up on Thursday. You have a couple of days to do that. All right, I will see you next week. I think maybe I'll see most of you here in the lab Wednesday for your second to last lab. Okay, your last lab will be the lecture that I'm going to do later on next month. All right. All right, thank you, everyone. If you have any questions, I'll be available. I'll also have office hours Friday. Saturday. Okay, Saturday, just reserve some time, and I appreciate that. Thank you.